Good afternoon, everyone. This video is going to be about marketplaces. So we're going to write a smart contract that supports 4 different types of listings. The first type of listing will be asset for Algorand. So user A deposits an asset into the contract as an escrow and indicates how much Algorand they want in return for that asset. User B comes in, deposits Algorand into the contract, receives the asset, and the Algorand gets forwarded to user A who made the listing. The second type of listing, same concept, but it's going to be asset for asset. So user A inputs an asset, indicates what kind of asset they want in return, and user B fulfills that. They both get each other's assets. And then the third type of listing is going to be asset for asset quantity. And this is, for example, like if you listed an NFT and you wanted X amount of another asset for it. So it's not one-to-one. So it's like NFT for 100 USDC. And then the fourth type of listing is going to be asset quantity for asset quantity. And this is where kind of like a limit buy or limit sell on an exchange. You have X amount of an asset that you want in exchange for another X amount of an asset. So if I had 100 USDC and I wanted 100 Yieldly tokens in return, I would indicate that in my listing request, and then user B will fulfill that. Similar concept as the other 3 listing types. So we're going to get started with writing the contract. So first things first, if you're new to this tutorial series, at the beginning of every video, we take a minute to quickly set up our private variables in a .env. We generate an account, we fund it with testnet, and we also import our launch smart contract template, which is how we deploy our contract onto the network. So I'm going to quickly do this .env, and we're not going to go over installation. This would have been in the first video of the playlist called installation. So .env, we're going to define our Algo token, Algo server, and Algo private key actually. And then we're going to create a file called generate account.py from Algo SDK.account, import generate account, private key, address is equal to generate account result, print private key and address, run this code. And we're going to take the address that's generated, go to bank.testnet.algorand.network, on the account, check off I'm not a robot. Then we're going to go to nodely.io, go to quick start. Down here under Algorand endpoints, second row, second column, copy the Algod public API for testnet. And in our .env, we're going to paste in this link under server, Algod server, and then the private key will go under private key. And the Algo token is always blank for the public API. We don't need to generate it. We don't need to generate an account anymore. So the next thing we're going to do is define our launch smart contract.py file. And we're going to just grab a template. You'll find this on the website if you're following along on the website. Mine is right over here. I'm going to paste this in. And the only thing we're going to need for global and local state is going to be 1 byte slice. Everything else can be 0. And remember to change the name of your approval and clear teal file names to be the name of your contract, which we're going to get started with now. So my marketplace contract.py. As always, from AlgoPy, import arg4 contract. From algopy.arg4, import ABI method. And we're going to define our contract here. We're going to call it listings, as I have defined here in my launch smart contract. And we're going to pass an arg4 contract. And then we're going to initialize, pass in self, return none. And before we get started with writing the contract, I have to introduce a new concept, and I'd like to also pass in all the dependencies and instances that we're going to use. So we're going to use arg4 contract, string, group transaction, asset, transaction, global state, inner transaction, global, and box ref. And then for arg4, we're going to use ABI method, address, struct, and bool. And struct is going to be the new concept that we introduced today. And then I always import my arg4 uint64 in a unique way. And a struct is a way for you to, in an organized fashion, go to and from byte sequences and their original arc4 values. So for example, in the staking smart contract, and I'll just pass on the initialization for now so I could show you an example. A few videos ago, we made a smart contract for staking. And somewhere along the lines, we read from a box and we also wrote to a box. I'll just use the reading box example. And what we wrote was two values, two integers, uint64s. And uint64s, they're each 8 bytes long. And the first number represented the amount of algo the user was staking. And the second number represented the time that they initially staked. And what you might remember that you saw was value exists is equal to box ref of the sender of the transaction dot maybe, and the key was the transaction sender. And then the value, the first number was value 0 to 8, and the second number was value 8 to 16. And we use op.b2i on these values to convert the byte sequence to an integer. And this is fine if you're only working with two numbers. But let's say we had 4 integers, one string, one arc4 string, and one boolean. Now things get a little bit more complicated, and I'll try to encode this manually. It's going to look ridiculous, but I guess that's the point, to show you why we use structs. So we would do this for 4 numbers, and we'd use 16 to 24 here for the third number, 24 to 32 for the fourth number. The string length would be the first 2 bytes of the string portion, so that would be op b2i. I'm not sure if this would work with a uint16, but we'll just use this here for the example. And then the actual string would be a string instance from bytes, and we would pass in value and the 34 starting index, and then we would stop at 34 plus string length. And then for the boolean value, we would use value 34 plus string length, and this would end at 34 plus string length plus 1. And this looks just ridiculous. And you will go mad trying to encode and decode byte sequences one by one like this. And this is where structs come in. So for example, if I had a class that said all this stuff, for example, and I passed in a struct here. Let's just use the consistent naming scheme here, all this stuff. And I wanted to use a first integer, which is an arc4 uint64, second integer, arc4 uint64, third integer, arc4 uint64, fourth integer, arc4 uint64, my string, which is going to be a string, and then lastly we have a boolean value, which is going to be a bool type. So instead of manually decoding, and I'm going to copy this, I could actually use that code I wrote before. 1 second, please. Okay. So instead of doing all of this, I'll just comment it out so you can see the difference in length and how much more legible it is. Instead of manually converting all these pieces, all these byte sequences and indexes, I can just say the box values is equal to an instance of all the stuff from bytes, and then pass in value. And now I can directly access box values dots, my first integer, my second, my third integer, my fourth integer, my string, and my boolean value. I don't have to manually encode or decode all these values at specific indexes, make sure I'm picking the right index, using the right starting point and ending point. Structs are important. They make your life much, much easier. And we're going to start, now that we have a good understanding of structs, I feel, with our listing contract, our marketplace. So before we get started, we need to define our box names and box values as structs. So there are 4 listing types, as I mentioned. There's going to be asset for algo, asset for asset, asset for asset quantity, and asset quantity for asset quantity. So for all the box names across the board, for all different 4 types of listings, we're going to use the same struct for the listing name. And this is going to just be the address of the person making the listing, and then a unique identifier or counter that's going to be incrementing per listing. So the first listing ever in the contract is going to be someone's address and the number 1. And the next listing that ever happens will be someone's address and listing number 2. So it'll be impossible for any 2 box names to be the same. Because if I use something like lister and asset, which you can't use asset in a struct, but just as an example, or we'll use asset ID, and then we can use arc4UN64. Let's say this person lists, they have 2 NFTs, they list one for 50 algo, and then they list a second one for 50 algo. The box names will be the same because it's the same NFT, just different algo prices. And so we're going to get a box name conflict here, where a box already has that name. And then if we did something else, like the algo requested, how much they're trying to charge for the asset, this would also be an arc4 UN64, we can also get a lot of conflicts. So the person who's listing the NFT or asset, they might say, hey, I want 50 algo for this. And then they go to list a completely different NFT, different asset ID, but they say, I also want 50 algo for this. You have another box name conflict because it's the same lister and the algo amount they're requesting is the same. So what we do is use the counter, which gives a unique identifier which will never repeat itself. So the box schema is going to be, for the box names, is going to be the same across the board. And now we're going to define the 4 structs for the different types of listings. So the first one is pretty simple, and we'll just call it listing value. And this one's just going to be the asset listed, which is the asset ID. It's a number, arc4UN64. And then we're also going to use the algo amount they want for that asset, which is another number. And this is going to be the value to the box, not the box name, the box value. And then let's say it's going to be asset for asset. We're going to call this a trade listing value, also a struct. And we're going to do the same thing here. Asset listed, arc4UN64. Algo requested is not going to be in here. We're going to use asset requested. And this is going to be the asset ID that they want in return. And then also we're going to add fulfilled, which is going to be a bool. And the reason we do this is because if someone lists, let's go back to this box and see that there will be no issues of not using a fulfilled. So if I list an asset in the contract and I say I want 50 algo for this asset, and someone comes along, sees the asset, and they say, yes, I'm going to purchase this asset, I'm going to send 50 algo, I'm going to get the asset, I'm going to opt into the asset, and then the contract can just send the algo to you. It's perfect. That's fine. No potential issues. For asset to asset, let's say someone sees the asset listed, they have the asset that I want, and they say, okay, I'm going to send this asset to the contract. I'm going to take their asset after I opt in, and then the contract is just going to send the asset I'm putting in to the person who made the listing. What if the person who made the listing did not opt in to the asset requested? The application call to fulfill the trade will always fail. And the only way it would ever pass is if you manually communicated with this person and said, hey, I can't purchase your item with my item because you're not opted in, and the transaction keeps failing. So the reason we have this fulfilled is because we're going to separate the lister, the person creating the listing, we're going to separate him selling the asset with him claiming the asset. So he can list the asset, someone can purchase it. For them to claim the asset that they received in exchange for the asset they listed, they have to go to the contract and pick it out. And that way we will always know that they're opted in, because to claim it, they need to opt in. That way, the person who's purchasing or trading can receive the asset they wanted right away, and they don't have to wait for the other person to opt in. And the fulfilled bool is going to allow the lister to retrieve the asset and confirm that it's been completed. And you're going to see this in practice after we define these here and finish with the listing value example. The next listing type is going to be asset for asset quantity. So we will call this something super specific. So trade listing value with asset quantity. And this will be a struct. And we'll need to follow a similar schema. So arc4uint64 for the asset ID listed, the asset requested, arc4uint64. And then we're going to add asset amounts requested. And then the fulfilled Boolean again. And again, the difference between these two, in this first trade, it's 1-to-1. So one asset for another asset. In this trade, they want one asset. They want to trade one asset for X amount of another asset. So if you have an NFT and you want tokens in return, like 100 tokens, 100 USDC, you would use this listing type. Okay, so we place into the struct here how much of the asset requested we want in exchange for the asset listed. And the last one we'll call trade listing value quantity with asset quantity. And again, as I explained before, so let's just fill these out first. Asset listed, arc4uint64. Asset listed quantity, arc4uint64. And then asset requested, arc4uint64. And asset amount requested, arc4uint64. So we're going to list X amount of an asset, and in return we want X amount of an asset, or Y amount of an asset. You can list 10 NFTs in exchange for 20 tokens. And NFTs is actually a bad example. You could list 10 tokens in exchange for 20 tokens. And there are different tokens, obviously, in this situation. But it's not fair to say 10 NFTs, because NFTs typically have unique asset IDs, and this contract does not support several different listings combined under one listing. So if I had 10 unique NFTs and I wanted these specific other 5 or 6 NFTs, that's not really, something you would ever see. But now that we've defined our 4 listing values, we can start with, first of all, we're going to put in our listing counter. And this is going to be a global state of an arc4uint64 starting at 0. And we increment this by 1 each time. Let me just lower this a bit. And this is the counter I was referring to up here for the listing names. So for any listing to occur, they need to send the asset to the smart contract. So the first thing we're going to do is create a method that allows users to call the contract and request that it opts in to an asset that we're about to send it to hold as an escrow for our listing. So I want to sell someone something, I'd like you to hold it so that you're ready to accept payment in exchange for it, and I can come back to claim it, or you can forward it directly. So for this trigger opt-in method, we obviously need to pass in self. We need to know which asset to opt into. And this is going to be an asset argument. So we're basically just going to pass the asset ID as an argument to this method. And then we're also going to need the fee payment for the opt-in and submitting the transaction. So this is going to be a payment transaction as an argument. And then we're just going to return a string at the end, and it's going to be successfully opted in to asset. And if we wanted, we could return a tuple string, and let's also return a arc4 uint64. And actually, let's return a uint64. So we're going to go up here, import uint64. That way we can pass in here we got our colon, the asset to opt into .id. And what am I missing here? Is it the indent? It's the indent. And we're good here. So the first thing we should do is assert that the fee payment amount is greater than or equal to 101,000 microalgo, because each asset opt-in requires 0.1 algo, and then we also need the transaction fee to submit, which is 1,000 algo. So we're going to submit our transaction right below this. Asset transfer, itxn.asset transfer, and we only need 3 parameters defined. The first is going to be the asset that's being opted into, which we're passing in directly here from asset to opt into. And then we're going to need the asset receiver, which is going to be ourselves, the contract, global.current application address, and the fee we can just set to global.minimum transaction fee. And then obviously we want to submit this, and we are good for the opt-in transaction. That's it. And we can even add a little colon here so it looks a little more continuous. So we can test this out before we do anything else by creating an arbitrary asset. So create arbitrary asset.py from Algo SDK v2 client.algod, import algod client, and from Algo SDK.transaction, import asset create, or we can also just use asset config transaction. So we're going to need our private key. Well, we're going to need our client as well. So algod token is equal to os.getEnv, algod token, need to import os. Algod server is equal to os.getEnv, algod server. Algod client is equal to an instance of the algod client, pass in the token and server positionally. Then our private key is going to be os.getEnv, private key. And we're ready to construct the transaction and submit it. So our asset creation transaction is going to be asset config, and we're going to pass in ourselves. We're going to need an address. So from Algo SDK.account, import address from private key. And we'll define address here. Address from private key, convert our private key to an address. So address for sender. For parameters, or SP, suggested params, we're going to get that from our client. So params is equal to algod client.suggested params, call that function. Pass in params. An index we don't have. If we're reconfiguring this asset, we would pass in that argument. Total, we'll say 10, so that we could do this multiple times. Let's do 20 or 100, why not? Default frozen, we'll set to false. Unit name and asset name. So for asset name, we'll do test asset 1. For unit name, we'll do TA1. And manager is going to be ourselves, reserve, ourselves. We don't need a clawback or freeze. We don't need a URL. There will be no image, no arc standard, and strict empty address check must be set to false. And we're going to say sign transaction is equal to asset creation transaction dot sign and pass in our private key. And then the transaction ID is going to be the results of submitting that transaction. So send transaction singular and pass in the signed transaction. And we'll print the transaction ID. We're going to wait for confirmation, and that can be imported from the transaction library up here. And wait for confirmation, pass in our Algo client and the transaction ID. And then once that's finished, transaction info is equal to Algo client dot pending transaction info and pass in our transaction ID. And once the transaction has been successful and confirmed, we can then get the transaction info and it will have the index that was created, the asset ID. And that's what we want so we can actually place it in our .env. So we're going to create asset 1 and asset 2. And let's run this code twice. I'm assuming there will be no errors, but let's see. Okay, perfect. So we got our transaction ID. It's waiting for confirmation. And then we just got, oh my goodness. We printed the transaction ID twice. Just rerun this. And we're going to run it 2 times. So here's the transaction info, and you see the asset index here. And you can even use key notation here for the future. So we can just get the asset index directly. We have our first one. We should change this to asset ID. So we have our first asset. And then our second asset is popping up now. There we go. And we're going to create our application client. We're going to call this opt contract. We're going to indicate one first. Opt contract into asset.py. So we can keep track of where we are in the process. So for the application client, from Algo SDK or from AlgoKit utils, import application client. And then we're going to need everything that we typically need here. We'll just type it out manually. Let's go back here. From Algo SDK.v2 client.algod, import algod client. And actually, I'm going to copy and paste this stuff here. So we have our algod token, algod server, my launch smart contract has a few things off here. That's fine. Just correct that. Okay, so let's start constructing the app client. First thing we need is our algod client. So algod client is equal to algod client. The next thing it needs is the app spec, which we don't have just yet because we didn't compile our contract. Let's go back here. So AlgoKit compile py my marketplace contract.py as you have it named here. And let's see if we have any errors actually. I don't believe we will. Yep, we're good. And we're going to pass in our app spec. And our app spec, we usually use path. So I'm going to state here, from pathlib, import path. And the app spec is equal to path underscore underscore file underscore underscore dots parent forward slash dot forward slash, because we're in the current directory, listings.arc32.json. Then we can pass this app spec in here. And I know we've done this several times, so you can skip forward if you want to fast forward a bit. Next up, we need an app ID, and we would need to launch our contract for that. So let's go to our launch contract, make sure approval and clear-teal file names match as they do here. So listings is what I have as a prefix. And then make sure that your global state and local state, so global state, we're only going to use byte slices. So we need 1, and everything else can be 0. And we can run this, and then paste the app ID we get out, and put it in here in our .env. App ID is equal to, and grab that here, put it in there. Go back to our opt contract into asset, where we're constructing the application client. And we're going to import our app ID, os.getEnv, app ID, as we named it here in our .env. Next up, we're going to need a signer. So we're going to have to import the signer. So from Algo SDK.atomic transaction composer, import account transaction signer. We're also going to need transaction with signer and atomic transaction composer. So signer is equal to, and we'll define our signer right here. Signer is equal to account transaction signer and pass in our private key. And then we're going to need, after signer, the sender, which is our address, and suggested params. We're going to grab that now. Params is equal to algo.client.suggested params. And that's pretty much it. So down here, we're going to instantiate an atomic transaction composer by just calling one. And then we're going to compose our first method call. So we pass in the atomic transaction composer positionally, and then call ABI method argument is going to be the name of our function here, trigger opt-in. It's also stated here in the arg32.json, trigger opt-in. And you can see the two arguments we need to pass, asset and a payment transaction. And then it states here that it returns a string and a uint64. So we're going to pass in a string for the name of the method. And then we can start putting in our arguments. So in the arg32.json, if you scroll down right here, you have the function and the names of the parameters. So I named this one asset to opt into for the asset. And for the payment transaction, I named it fee payment. So I'm going to grab the first argument and define that here. Asset to opt into equals. And we're going to be listing this first asset that we made. So we're going to go and import this. So asset1 is equal to os.getEnv asset underscore 1. And the asset to opt into will be this asset. The second argument is the fee payment, as it's called. And this is going to be a payment transaction. So fee payment equals, and then we need to construct this payment transaction before we compose the call. So we'll say here fee payment transaction is equal to payment transaction, which we need to import from the transaction library. And the sender is going to be us, our address. SP is going to be the params that we already defined. Receiver is going to be the address of the smart contract. And what we should do, and this is why we have an upcoming video for security, is we should assert here that the fee payment dot receiver is equal to the global application address, this application. And while we're here, I'll just quickly compile this. Control S to save, press enter. And I'll paste in the new app ID. So we can have that update once I launch again. Perfect. Okay, and we can get app address directly from the application client. It's an attribute here. For the amount, we stated that it must be greater than or equal to 101,000 algo. So I'll just do the bare minimum because testnet is not very busy right now, and the fee will likely not be higher. And then that's pretty much it here. And then we need to wrap this payment with a transaction with signer and just pass in the fee payment transaction and our signer. And wrap payment goes right here for the fee payment. And then we can results is equal to, we can execute atc.execute, pass in our Algo client. Let's wait 2 rounds, or we should call this results. And this is always tricky to me, but it's so we're gonna get the transaction IDs and list comprehension. So results dot transaction IDs I for I in range of length of results dot transaction IDs. Yes. And then for the ABI results, similar concept. So results dot ABI results I for I in actually I dot return value for I in range of the length of ABI results. And I think I walked you through this in detail previously, but this basically just gets all the transaction IDs that are output from our execution and all the ABI results that are output, and it prints them right here. And I believe this should error because the asset 1 should be an integer, and that's exactly what happened. So when we read from a .env, it is a string by default. So we need to convert this to an integer when we import it using os.getEnv. And same thing with the app ID. So I just went up here to where we imported the app ID and I converted it to an integer. And you can see our contract successfully ran. We have 2 transaction IDs. So the first one is going to be the payment transaction. The second is going to be the application call. And there's an inner transaction within this transaction ID, which is where the contract opted in to the asset. And you can see the ABI result here successfully opted into asset. And the asset ID that's opted in is this asset 1, which we created. We can take this to Laura. Oh, not here. And paste this in here, make sure you're on testnet. And you can see here that there was an application call. Actually, where's the group? Here. So you can see there was a payment transaction, which was the fee for the opt-in, and the contract also sending that opt-in transaction. So the payment, the app call, and the inner transaction where the contract opted into the asset. I just did a 0 amount transaction to itself, transfer to itself. Then we're going to go back. Where were we? Here. And we're going to add to our contract our first listing request. So we're going to call this method def post listing request. And we're going to pass in self as always. And the user is going to send an asset. So asset to list. This is going to be an asset transfer transaction. And we're also going to have them state how much algo they want for this asset. So we're doing this first listing type here, where they list an asset and they state how much algo they want in return. So the algo amount requested is going to be a number that they tell us, or the contract. And then they're also going to need to pay a box fee. because as we went over in the box references videos, there's a fee for creating a box. There's a 2,500 microalgal fee for just creating it. And then there's a 400 microalgal fee per byte used in the key and value. So let me just finish up this type annotation so I could show you how much we're going to need for this one. And this is going to be a payment transaction. And we're also going to return a string and a UN64. And we'll even return string UN64, string UN64. So it's going to return asset successfully listed, the asset ID. User is requesting X amount of algo, and then the algo. So for the box fee MBR payment, we want to assert that the amount is equal to how much the contract will need to actually create and host the box. So we have our calculator here. So if we go up here, our box name is going to need 32 bytes for the address, and then 8 bytes for this arc4 UN64. So already we have 32 plus 8 bytes. And then for the listing value, we're going to use 2 UN64s. And that's going to be 8 plus 8, so 16. So we're using a total of 56 bytes for this box for the name and value. So that's going to be 56 times 400. So 22,400 microalgo. And then, of course, there's the fee for creating a box, which you only pay once, which is 24,900. So we need to assert that the box fee payment they're making is equal to 24,900. And we can't use commas in Python, so I'm going to put an underscore for the comma separator. So now that we've got that out of the way, we're going to, before anything, increment our listing counter by 1. And we're going to do this by creating an arc4 UN64. And this is going to be composed of the current listing counter value. And we'll use .native, so we can use arithmetic with a native integer here. And then we're going to construct our box name. So the listing box name info is equal to an instance of our listing name struct up here. Let me just pull this down. And our listing name struct only needs a lister and the counter. So the first thing we're going to input, and we'll use positional arguments, will be the lister, which is the sender of this transaction. And this needs to be an address type, as we indicated here. But transaction.sender gives you an account type. So we need to manually convert this by passing this into the address class. You can see here, address takes an account and produces an address value. And then the second one will be the counter. And that's just going to be the current listing counter dot value. Next up, we're going to create a box. But first, we need to create a reference to the box. So listing box is equal to a box ref, where the key, which needs to be in bytes, will be listing box name info, which we just created, dot bytes. It's that easy. We don't need to decode the address and decode the integer. We just convert the struct into bytes. And we're going to return the tuple of whether or not it has a value and exists is equal to listing box.maybe. We can assert that it does not exist, but it is impossible for this to exist at all because the counter always goes up by 1. But but we'll just put this in as a security feature, never know. And then we're going to create the box. And we're going to input the size that we're going to need for this box. How many bytes will this box need? And this box is only going to need 16 bytes. And this is because it's only referencing or referring to the value of the box. It doesn't care about the size of the name. It just wants you to define the size of the value. And this is going to be fixed at 16 bytes, as we have it arranged here. The asset ID for the asset listed and the algo amount that they're requesting for this asset. So two numbers, two UN64s, 8 bytes each, total of 16. Next, we're going to create the value. So the value for the box, listing box value, listing box value info is equal to listing value instance. And we're going to pass in the asset that they're listing, asset to list, which we're fetching here from this asset transfer, asset to list, acts for asset. So the asset that's being transferred in this asset transfer transaction. And this needs to be converted to an ID. So it can be a UN64. But even then, we need to convert it into an ARC4 UN64. The ARC4 UN64 is the only one that supports being converted to bytes directly. Otherwise, you would need to use op.I2b, integer to bytes. So after this, we will also need an ARC4 UN64 instance of the algo requested. This is passed in and interpreted as an ARC4 UN64, so we can just pass this in on its own, like so. Then we can put this value into the listing box. Listing box dot put, and then listing box value info dot bytes. Now that we're done here, we're going to return, and we said we'd return a string with the asset ID listed and the amount of algo requested. So we're going to return here string user listed asset successfully. And then we'll pass, we'll return here the asset to list dot acts for asset dot ID. And then we'll also put here user is requesting another string, X amount of algo. And then the next one will be the algo amount requested. And we should indicate here that the algo amount requested, actually this works fine. I believe this should work fine. We're going to give it a try and see. Just to be safe, we'll do this. And let me just double check here. There's one thing we didn't include. If this asset transfer was of an amount of 0, so I'm sending an asset to someone, I'm creating an asset transfer transaction from myself to the contract, which we'll assert here. Assert asset to list dot receiver dot asset receiver is equal to global.current application address. But we also need to assert that the asset amount is equal to 1. Because they could do an asset transfer of 0 and this contract would not know any better. So we need to make sure the contract knows, double check that they're actually sending something. Otherwise, you're going to accept a listing with no asset. And we should be safe to compile this now. going to press up in the terminal until I find my AlgoKit compile. And my terminal looks messy. Don't worry about it. I don't know why it's been doing that lately. We have our new contract. Going to launch it. Paste a new app ID once we get it here. And we're going to copy and paste our opt contract into asset. And we're going to change the name to list in asset.py. And we need to combine this application call with the listing. So we need the user to call both methods at once. They need to opt in the contract to the asset and then post the listing request. And this is going to be a single group transaction. You could do it separately, that's fine. But we like to live life on the edge. We're going to do both at once. So appclient.composeCall, ATC, call ABI method, and the name of our method is post listing request. And put that as a string. And it requires 1, 2, 3 arguments. And if we go to our arc32.json, or you could read from the code directly, you can see the variable names that we need to pass in. Let's go back to our number 2 here, list an asset. And before we compose these calls, we can put the arguments in. So asset to list will be the first one we pass. And this will be, and let's actually keep these separate. So assets to lists transaction is going to be an asset transfer transaction, which we import from here, from Algo SDK.transaction. And the sender will be ourselves. SP will be params, as we already have it. Receiver will be the app client.app address. The amounts will be 1, as the contract wants. The index will be our asset1 index. And that's pretty much it here. And then wrapped asset list transaction is equal to transaction with signer. Pass in our asset to list transaction and our signer. So now we have our asset to list. Parameter completed. The next one is algo amount requested. And this is just going to be a number. So let's say we want 1 algo. That would be 100,000. Oh, excuse me, 1 million. And if you're not sure, you can use the from Algo SDK .util import algos to microalgos, and you could do it this way as well. So we're going to want 1 algo, and the next argument is the box fee MBR payment. And in here, this doesn't need to be greater than or equal to because the box fee does not fluctuate. They may one day change the box fees structure, but hopefully that day does not come soon because a lot of contracts have hard-coded the box fee MBR payment standards for their contract, the amounts they want. So we're going to do the same thing we did up here. We'll just rename this to box fee payment. And we'll include here wrapped box fee payment. And we'll make sure that we use the amounts that we stated here in the contract so that it doesn't fail. Great. And we wrap this up here and pass it in to our, this needs to be above our compose call for post listing request. And now we pass in our last argument here and the name of the variable again, box fee MVR payment. Is equal to, and pass that in here. And if it gets a bit long, what you can do is press enter here so you can see everything clearly. And we can do the same thing here, why not? And we should be good. And now we should see 2 ABI results. Let me just clear this here. And let's give it a shot, see what happens. Might get an error, who knows? Transaction already in ledger. And why is that? Here. We need to pass in the box fee payment transaction, not the fee payment transaction. And we get an invalid box reference. So we need to remember to include the box reference. So we're going to pass this in here. Transaction parameters is equal to a dictionary. And we're going to pass in boxes. And the box that we're going to pass in, we know the structure of the box name is going to be an address and a counter. And I guess we should probably try to make this scalable. So how do we know the current counter? We could get the global state of the contract. So the global state, or let's say current global listing counter, is equal to the application info method of the Algo client for this app ID, and we can get it from the app client.app ID, yes. Or we can get it directly from our os.getEnd. And we're going to get params followed by global state. There's only one global state, so it should be 0, the first index. And then we need the value and byte schema. So we'll print this so we can see. It will be 0. But what we need is going to be the counter plus 1. So current global listing counter, because in our contract, the listing counter gets incremented by 1 before it gets used in the listing box name info. So we're going to set the current global listing counter. We're going to need a coder. So let's use a UN64 coder. And we're going to need the ABI type. So from Algo SDK.ABI, import ABI type. And ABI type.from string, tuple string UN64. And then we're going to base64 decode this current global listing counter. And I'll print this here, base64 decoded global listing counter is equal to b64 decode, which we'll need to import from base64, import b64 decode. Current global listing counter. And then we're going to encode. So encoded global listing counter is equal to UN64 coder.encode and actually decode the B64 decoded global listing counter. And then here you will see the 0, and I'll print these steps here so you can kind of see what's going on. So printing the counter, B64 decoded, UN64 encoded, and then the listing box counter will be this encoded global listing counter plus 1. And then we'll create a coder, listing box coder is equal to ABI type dot from string and a tuple with address and UN64. And then we can state here users listing box is equal to listing box coder dot encode and pass in a tuple with our address and the listing box counter. And we'll get a byte format of the box name to be. It's not actually created yet. And then we can pass in this into our boxes argument. And the boxes key requires a value that is a list of lists. So we create a list, and then within it we have a list with the first index or the 0th index as the app ID, and the second position or first index will be the box name. Let's call this box name. And we should now not have this error anymore, but let's take a look. Rename this here. And let's see here. Can only concatenate list, not int to list. And that is because when we use the ABI type to decode, we receive a list of results back. So we need to access the first results, which will be that integer 0. And you'll see here, we get the current global listing counter, base 64 encoded. Then we get the base 64 decoded version, which is 8 bytes. Then we get the number, which is just 0. And then we get our user listing box name, and it looks like a mess of bytes, but this is essentially our address from here to here, 32 bytes. And then the last 8 bytes here is the number 1, so 0000001. And this is what the number 1 looks like as a UINT64 decoded byte sequence. And then here you get our transaction IDs. So we have our first transaction. I'm just going to remove these print statements. Our first transaction is the payment transaction that funds the contract for the opt-in. The second transaction ID is the actual opt-in. The third transaction ID is this asset transfer transaction. The fourth transaction ID is this payment transaction for the box fee. And then the last transaction ID is going to be this application call here. And you see our ABI results down here. We have 2 sets. So the first set is from the opt-in method, successfully opted into asset, and the asset ID we had the contract opt into. And then the second one, user listed asset successfully, the asset ID, and then user is requesting X amount of algo, and you see in micro algo the amount of algo they're requesting. And you can see here we can take any one of these transaction IDs, go to LoRa, paste it in, click the group, and we'll see our wonderful group transaction here. So these first three These first three up here are for the opt-in, for the contract, and paying the contract. And then these last three are for transferring the asset, paying the box fee, and then actually creating the box. And if we go to our app ID, which is up here, you can see that there is now a global state. Obviously, we have that already, but we also have a box. And this is the name of the box. And here you see the box value. And if we decoded this box value, it would be the asset ID that we listed, as well as the amount of algo requested. As we formatted here. And we can confirm that this listing has been posted. We'll create a new file here. Check boxes.py. And we're going to import a few things here. We actually just need the Algo client. Let me grab one from here. Okay, perfect. And then we'll also need the app ID. And then the boxes in the contract is going to be equal to application boxes method of the Algo client. And we're going to pass in the app ID, and you see it wants an integer. So we're going to convert this into an integer before we use it. And pass in the app ID. And we'll print the boxes here. And you see there's only one box in here in this list. So we're going to access boxes and the first one there and get the name. So we can call this only box or just box. Name B64 encoded. And this is going to be the sender address or the lister address, followed by the number 1, and this is base 64 encoded. And we can use our box coder to get the information, which we have right here. Import API type from the API library. And we're going to need to input. So it's going to be decode. And we're going to input the bytes, which is the base 64 decoded. Need to import that as well. Version of the box name B64 encoded. And we'll get here the tuple with the address of the person who listed and their unique counter value for their listing. So we're going to try, and we're going to copy and paste our list and asset file here, and we'll call it fulfill listing request. And before we start messing with this, let's actually add this to our contract. So we have a post listing request, and now we need a fulfill listing request, where someone will pay that amount of algo, receive the asset, and the algo gets submitted or forwarded to the original lister. So we're going to create a new ABI method, def fulfill listing request, and we're going to pass in self. We want them to indicate the asset listed to make sure they know what they're buying, the listing name, so that they can also confirm the listing they're referring to for this asset and the price. We want them to send a payment, so a group transaction for payment. And then we also want them to pay a transfer fee. And for this scenario, it's going to be, and we're going to return a string here. And for the transfer fees, we only need them to pay enough for the contract to submit two transactions. The first will be an asset transfer to the purchaser of the asset listed, and the second transfer fee will be for the payment transaction for forwarding the algo sent to the contract to the lister of the asset. So assert the transfer fees or payment transaction, the amount is equal to 2000 microalgo. And then we can start referencing the box. So the listing box is equal to a box reference where the key is the listing name that they're passing as an argument here as bytes. And then we're going to confirm it exists. Value exists is equal to listing box.maybe. We can assert it exists, but this will fail either way if it doesn't exist. And then we want to assert, well, first we want to get the bytes. So the listing value is going to be equal to listing value dot from bytes. So what we're doing is we're getting the information in the box value and constructing it into a listing value class from the bytes in the value of the box. And then we're going to assert that the listing value dot asset listed is equal to the asset that they're requesting. And we need the UN64 version of this. And we're also going to assert that the algo amount requested is equal to the amount that they're sending in their payment transaction here. And if we don't assert this, we wouldn't authenticate that the asset listing is the asset that they want. And we wouldn't know that the amount that they're paying is actually what the listing is requesting. So someone could send one algo, and without this line of code here, the payment would be fulfilled, and it wouldn't care how much the lister indicated they wanted. And then that's pretty much it for authentication. We can now pay the lister, and this is going to be from listing name dot lister. This is going to be an address. And then we can also indicate here the amount we're going to pay them will be the amount sent. The amount sent in the payment transaction, which we know is equal to the listing value algo requested. And lastly, we need to define the fee, so the minimum transaction fee. And we want to submit this inner transaction for payment. And then we want to send the asset to the person purchasing the asset. So we're going to define the asset ID. The X for asset will be the listing name, or actually, we have this here. We can either get it from asset listed, or we can get it from listing value dot asset listed. Either one works. I'll just use asset listed. And then the asset receiver is going to be the sender of this transaction, the person making the purchase. The asset amount will be 1, because for this type of listing request, the first type, it's asset for Algo, and there's only one asset. Later on, we do multiple assets, so this might be 5 later on for X amount of Algo. And fee is going to be, again, the minimum transaction fee. And we want to submit this. And once this listing is fulfilled, the sale request or the listing request, we don't need the box anymore, so we can just delete it. And we'll return a string, and we'll state listing fulfilled. And we can even do a tuple here. So it'll be a string, and we'll state here listing fulfilled for asset. And then we'll put in here the asset listed. That's going to be a uint64 asset listed.id. And then we'll also state another string here. Lister received X amount of Algo. And then we'll include the payments.amounts. And that will be another uint64. And let's compile this, make sure we don't have any errors. My marketplace contract.py, as I have named here. Oh, I'm not sure if I saved this. Oh, we get an error here. Argument receiver to payment has incompatible type address expected accounts or string. So this is going to be here. And what we can do is wrap this. Or actually, we can get the native version. And I believe this will present an account to us. And it does. So now that we have a method to fulfill a listing, we can start writing our fulfill listing request.py. So the first thing they'll have to do is opt into the asset. And we should probably include this. So in our marketplace contract, we're using the same address that generated these 2 assets, so they don't need to opt in. But we should probably opt in during this request. And I'm just going to delete from here. We're going to remove this compose call. We're not going to need a box fee payment. We don't need to know the current counter. And we do need a fee payment. We don't need to trigger an opt-in. And we don't need an asset transfer. We do need the listing box coder. And we should be good here. So the fee payment for this instance, for fulfilling the listing request, will be for 2,000 microalgo. Then we'll also need a payment transaction. So the listing is for 1 algo, the asset. So we're going to create a second payment transaction here. And this we'll call asset payment transaction. So they're paying for the asset. And we're charging 1 million microalgo or one algo. So we have these two things out of the way. Then we need the listing name. And we can get this by manually encoding the address with the counter, which we know is 1. So counter is equal to 1. And then we already have an address value. Whoop, I'm in the wrong file. And then we already know the address and the counter. So the counter is 1. And the address we already have defined in our code here. But you could manually decode it as we did here, if you'd like. So we're going to state here the box name is equal to listing box coder dot encode, and we're going to pass in a tuple with the address and the counter. And we're going to compose a call here and pass in our atomic transaction composer, call ABI method, and we name this fulfill listing request. So we'll pass that in as a string. And in the arc32.json or in the My Marketplace contract, you can see the variable names here. So the first one is asset listed. So the asset listed is going to be equal to asset 1. And the listing name is the next variable, and this is the box name. So box name is equal to, and we have a variable here called box name. And next up is the payment transaction for the asset payment. And we're going to pass in our wrapped asset payment. We'll rename this. And then we have the transfer fees. So transfer fees is equal to fee payment, or actually wrapped. We'll call this wrapped fee payment. And then, of course, we need to pass in transaction parameters. And I'm going to just indent this so we can see this more clearly. And this is going to be a dictionary with keys indicating what parameters we're inputting. So boxes is going to be equal to a list of lists. And the first list, the only list, will be the app ID and the box name, which we have here. We're using it twice, one as an argument and one as a reference, because the contract does not actually have this resource available by default, so we need to pass it in with the application call. And this should be good. Oh, if this account was not the account that minted the asset, what you could do is create an asset opt-in transaction. And this will be an asset transfer transaction where the sender is our address, SP will be params, receiver will be our address as well, amount will be 0, and the index will be asset 1. And then we could manually state atc.add asset opt-in transaction. And this would actually need a transaction with signer. So we would state here wrapped opt-in transaction is equal to transaction with signer, pass in our asset opt-in transaction and a signer. But since we're already opted in, we don't need to add this into the group. And we can run this, see if it works. Oh, we need to relaunch our contract, get a new app ID, and start from list an asset. So we're going to list the asset again. The box name will be the same. Same address. Counter is going to be incremented by 1. And then we can try fulfilling this listing request. And unspecified argument listing name. Listing name, not box name. Kind of encode the following public key, 151. I see. So we don't actually need to decode this. We can just directly use the box name here, as we already are. But for the listing name, we're going to pass in the address and the counter as a tuple. We have an extra parentheses here. And now we're good. So for structs, when you pass them in as arguments, they need to be in a tuple format, like so. And we get a response here, so 3 transaction IDs. The first is going to be the payment transaction for the asset. The second will be the payment transaction for the fees. And the third is going to be the application call for fulfill listing request, which has 2 inner transactions. And we can take this to Laura and look at the group here. And we'll see our payment for the asset, 1 Algo, the fee payment, the application call, and this application call has 2 inner transactions. One forwards the payment to the lister, and the other transfers the asset to the buyer. And in this situation, we're using the same address. And what we could do is even, maybe we should do this. Let's create a second account. And private key, address is equal to generate account, print private key, address. We'll go to bank.testnet.algorand.network and put this address in here. And we'll create a buyer key. And then that way, we will use the buyer private key, or the buyer key. Let's call this buyer private key. And then fulfill listing requests, we'll use this as the private key. And then this second user will fulfill all of these transactions. And of course, this time we will actually need the opt-in transactions. So I'm just going to go back a little bit and grab this code we had before, and then go forward. And this is Control-Z and Control-Shift-Z. And now we're going to actually add this opt-in transaction because this user will not be opted in. And we need to pass in the wrapped opt-in transaction. And let's see how this goes. Oh, the listing was already fulfilled, so we need to list it again. And this time the counter will be 2. So we need to increment the counter to 2, since this is the second listing request. And assert failed. And the assert is failing because the listing box name is actually going to be the address for the original key. So we're going to go back here and we'll input this manually right here. So lister address is equal to address from private key os.getEnv, the original private key. And lister address will go here, and lister address will go here as well. And now our box name and our listing name matches the original address that made the listing. And since we need to submit a transaction to the original account, we must include that in the foreign accounts parameter. So in our transaction parameters here, we're going to add accounts, a list, and then pass in lister address. And now we should be good. Perfect. And now when we look at lower again, we'll see a more accurate depiction. So user B opts the asset, pays for the asset, pays for the fees, calls the method to fulfill the order. The payment gets forwarded to the original lister, and then the asset comes back to the purchaser. And this is a more accurate depiction. And now we're going to include a method to cancel a listing request. So let's say the person who made the listing changed their mind and they want to cancel it. So we'll create a new method, cancel listing request. And we want them, so pass and solve, we want them to state the asset they wanted to list so they can be sure that this matches the listing name they're thinking of. And then we need them to pay the transfer fee. And why is this occurring here? We are indented one space too many. And we'll just return a string for this one, listing request canceled. And we're going to assert that the transfer fee, that amount, is enough for the transaction to give them the asset back. Oh. And then we also need to assert that the person canceling this listing request is the lister. And we can just use transaction.sender. We're going to have to use native here so that the types match account to account. Then the box is going to be a box ref where the key is the listing name as bytes. Then the value exists is equal to listing box.maybe. We can assert it exists if we'd like, but this transaction will fail if it doesn't exist. And then we're going to get the listing value, which is equal to listing value, an instance of listing value, dot from bytes, and then the value of the box. And then we want to assert that the listing value dots asset listed, and this is going to return the UN64, is equal to the listing asset they're passing in, the ID of that listing asset, the asset ID. So number to number comparison. And that's pretty much it for verification. So we can now submit an asset transfer to give them their asset back. We can either use listed asset or we can use listing value asset listed. I'm just going to use listing asset.id. listing asset.id. And the amounts, asset amount will be 1. The asset receiver will be the sender of this transaction. And the fee will be the minimum transaction fee. Then we want to submit this. And we want to delete the listing box since they're removing the listing. And we'll return a string, listing request cancel. Now we can compile this. Make sure to save with your changes. And I'll show you this full code again, just in case you're still typing. And we'll add this, we'll copy and paste our fulfill listing request and rename this to _4 cancel listing request. And we'll only need a fee payment here. And this is going to be from the first address. So we need the original private key of the lister. The fee payment will only be 1,000 microalgo. We will need this, but it's going to be set to 1 because we're going to create a new contract. So the counter resets. And lister address, we can leave this here, but it will be the same address that we obtain here. And then we don't need this payment. Oh. We won't need foreign accounts. And let's look at the arguments here. So we need to pass in the listing asset. That will be asset 1. The listing name, which we already have prepared here. Transfer fees. We call this transfer fee, singular. And then we still need to pass in the box. And of course, we need to change the method name. And this should be good here. So what I'll do is list an asset after I launch a new contract. Replace our app ID and our .env. So we'll create a listing. And then we'll immediately cancel that listing. And I'm assuming there are no issues here. Let's see. Found 0 methods for cancel listing request. Strange. So let's try compiling again. Perhaps I did not save. Now if we look at our arc32.json, it was not here. So let's look at these issues here. Function is missing a type annotation. Line 132. And it's this right here. We put an equal sign for some reason. So let's compile, launch. Include the new app ID. List an asset. And then cancel the request, attempt number 2. And looks like we're good. It's processing. Perfect. And I'll go hit Laura, take a look at the group. And we see we made a payment and the app call, and we got the asset back. And if we look at the contract, we'll see there are no more boxes.